Okay, well, anyway, welcome. I really am glad to see you. And like I said, even though I've finished the grades for your class, this year is a little unusual. The good news, you did not have to take my exam. Some of you might look forward to, is that right? No. But no, I don't think anybody looked forward to taking exams. I think they are important to know that you had a whole semester worth of material. How much do you retain? And so to me, it was always good information for me. If I noticed that the average grade in here was like an 86 and the average grade on the exam was like 76, I'd have to look at that carefully. You see that? But anyway, I like to see exam grades, but you don't have the exam for the first semester. You will have one for the second semester. So the one thing I'm going to ask you to do, originally I had given people these file folders to put tests in, and I asked you to return those, and I think almost all of you did. I haven't checked your name off yet, but if I gave you a folder of the first semester test, bring all that to me, and I will set up a folder for the second semester. When I do, assuming that everything goes well and we are in school, then we will have an exam for the second semester, but my exam would only cover the stuff in the second semester. Does that make sense? So what I would do in the file folder is keep the next test we have would be the first amount of material that you would have to study for that test. Okay, so does that make sense? So go home. If you didn't return your file to me, and you have to, number one. And number two, I will start putting your new test in there, and I'll take the other ones out. I'll put the new ones in, and you'll just have to study that for the second semester if everything goes well. Now, I did want to start labs, but I'm going to have to back off on that a little bit. I know that my other classes are just now wrapping up their labs, and so there's also one more chapter we have to do, and if we finish that chapter, we would have a test on that chapter. Then I would come back and do about a 4-day lab, and then you would have a day where I review what you learned on the lab. And the 4-day lab is you'll go to every table and do real experiments, real reactions, and you'll try to classify them, you'll try to balance them, you'll like to make observations. And then I will take 1 day and review all the labs that you did in those 4 to 3 days, whatever. And then we would have a thing called a lab test, okay? Now, we had a lab test before, didn't we? Did we have a lab test? No, we didn't have one. That's right. A lab test is where I simply test you on what you did in the lab. And some people love lab tests. He says, I was there. You want to ask me what color copper 2 sulfate was? I was there. It was blue. And so I can ask that on a lab test. I also will tell you that whatever the questions on the lab test, I won't ask those on the second semester exam because you wouldn't have seen that chemical for maybe 3 months. See that? Or 4 months. So what we do is we'll take this chapter here, have a test on it, and you'll know enough information to understand the entire lab. And in the lab, you will go to 7 different tables and do 7 reactions. There might be one reaction that said, I love that reaction. I'm going to do it again. And you might want to do it more than once. And you can do them in different orders. And the idea is that when you do the reaction, you'll say, and I know what's going on here. I can explain what's going on here. Anyway, so we'll have a test. We'll do our lab test, and then we'll move on to one of the biggest areas of chemistry that some of you will fall in love with, I think. And it's called stoichiometry, which is the mathematics of chemistry. And we'll have about 3 chapters in a row where you deal with a lot of mathematics of chemistry. And at that point, you will be in very good shape. Even though we have more. You'll be in very good shape as far as being a first-year chemistry student. You'll be pretty up there, pretty high. Then when we get done with that, I have another lab. We'll do another lab there, and another lab after that. And then you will do quantum mechanics will be near the end of the year. We start talking about the periodic table and the idea of what is quantum mechanics, what's the new model of the atom, not necessarily the one you did in chapter 3. So that's what we're going to be doing in chemistry, and I have a good feeling. When I get done, I usually feel like that was a good year for first-year chemistry. Some of you, the way it is now, you can't take second-year chemistry until you're a senior. That's just the way it is. That's too bad, but some of you will choose when you're a senior to take a second-year chemistry. And I think we have about 17 in this year. The most I've ever had is 25. The least I've ever had is 12. But we have about 17 this year. And most of those people are people that say, well, I think I'm going to be doing something in science, maybe in engineering. I want a class that keeps me going a little bit. And so that's what we have now, the senior science. And they do a lot of neat things too. So, okay, long story short, we are going to start another chapter. And I do want to ask you, I'm going to tell you about something. I consider this chapter to truly be an honors level chapter. I think that you will be okay in it. You'll do well in it. You can do very well in it, but you have to do more than just pay attention. I certainly want you to pay attention, but I want you maybe a little bit of input. If you can, the more times you can raise your hand, the more. And we're all going to get in the book. We're going back in the book for chapter 7, and I am going to assign the odd questions. Remember that? How we used to do that? So instead of you just filling out the packets, you're going to actually be doing the odd questions for homework. All right, so what I'm going to do is we're going to start today, and just tell yourself, hey, today what we want to do is we just want to talk. We want to talk about chemistry, and we want to talk about this chapter. And no one's expecting you to remember everything we do today, but let me see if I can get it. There you go. All right. Excuse me. All right. Now the first thing, my TV's not ready, or my video's not ready yet. What I'm going to do is, the name of this chapter is called Reactions in Aqueous Solutions. And that's the first thing I'm going to draw your attention to. Why did they think this is important? And I'll tell you what I think, okay? How often does a chemist, someone actually hands them a chemical and says, can you react that chemical with that chemical? They don't do that very often. They're more likely to say, can you tell me what's in this? They want you to analyze something. Got that? When you get sick, and sometimes they'll take a blood sample. If you get another kind of sick, they might take a urine sample. Or if you're really sick, they might even take a sample of your spinal fluid. Now, I don't know, some of you may have had that before. They say, well, what the heck? Why are they wanting my fluids? And what is it in the fluids you think they're looking for? Well, if it was blood, it's possible I might be looking at your white blood count. That might be living things, right? I might be able to look for living things in blood. Your red blood count, your white blood count. But can you tell me what else they might look for in some kind of sample from you? Besides cellular, besides cells, what could they be looking for if the doctor wants some of your blood or your urine or spinal fluid? What could they possibly be looking for? And so we're just talking, okay? Has anybody known anybody that's had to give some kind of sample like that? And what were they looking for? Say it again? Cancer. Okay, now, if they take a biopsy, a piece of tissue, they're going to go in the microscope. They're probably going to stain the cells because they're looking for cells that look unusual shape. The cells actually are your cells. Cancer cells are your cells, but they're your cells that aren't acting like they're supposed to. If you have a lung cell that has a mutation, has cancer, it's going to maybe divide more rapidly than it should. Its shape might change a little bit, and it's going to probably outcompete the other lung cells. And so if you let it keep growing, it'll just, the real lung cells will die out, and you'll be replaced with cells that don't want to really be lung cells. But cancer is kind of like you. So I believe most of your cancer they're looking for is a cellular material. All right, what else? What else might they look for? I'm sure you had to have known somebody in your family that they were looking for something. All right. Has anybody, just raise your hand, you know anybody in your family that there was something wrong with the amount of iron in their blood? I would say most of you, no? Okay. So how do we do that? We take a sample of your blood and we put it next to your ear. Tell me, how much iron? No, they won't. And so where is the iron? Even if I looked under a microscope, am I going to see the metal called iron? I'm not. It's going to be in solution, okay? And it's going to be probably the metal ion. It's going to be the iron ion. You see that? What if they said, I think your potassium level is too low? Are they going to look at my blood and see that shiny, soft metal that you saw explode water? No. They're going to see potassium in the form of an ion. And ions are soluble in water. You see that? Almost all your ions are pretty much soluble in water. So if they're testing things for your blood, like copper, there's a disease that they have to test copper, or iron, or potassium, or sodium. There's lots of things they can test that are chemical in nature. What if you've been exposed to a certain kind of metal? What if you get those are usually poisonous, like lead poisoning. You can be poisoned by lead or mercury. And that also would be in the form of an ion, and it would be in solution. So most of the time, a chemist, if they're going to do their work on and find chemicals, chances are they're going to put them in solution and look at them there. So we're actually entering another level of chemistry. Got it? Whatever level you're in so far, right now, you can write formulas, you can balance equations, right? And that's great. We need one more chapter to finish that story, and then we'll tack on the mathematics on there, and then we'll complete the story that way. All right. Well, the first thing is something I introduced last chapter. What is it that makes a chemical reaction take place in the first place? Why? Why, when you put two chemicals, nothing happens? You put two other chemicals together, and something happens. And sometimes you have to put two chemicals together, and you have to heat them, and then something happens. Other times, like sodium and water, I didn't have to heat that, did I? Some reactions are spontaneous. I didn't have to do anything. You guys, the lab you're going to do, at least twice, you're going to use these burners. Very dangerous little burners are neat. And you have to make the reaction take place by adding heat. Why is that? So we have these things called driving forces, and I didn't ask those on the last test. I will in this test. What is it that tends to make a reaction take place? And these are just four of them, okay? One of them is the formation of a solid. One of the labs you're going to do is you'll start with two liquids. You won't see any solids. They're going to be two solutions, and they look like water. You're going to put them together, and you're going to see a solid form. That is a driving force. That's what made that reaction take place. Another one you're going to do is the formation of water. Things are dissolved in water, but what I mean is new water. Like not the water they're dissolved in. It's like some H over here and some OH over here is going to form water. Another driving force would be the formation of a gas. You'll be doing that one. You'll be doing zinc metal and hydrochloric acid. You'll make some hydrogen gas. You'll even test it like that. That's also another driving force. And then the other one, which I barely mentioned last chapter, but I'll have to mention more this chapter, is called the transfer of electrons, where something like a metal wants to lose electrons, and something like a non-metal likes to what? Gain, and that's what happens. And there's a transfer of electrons. Okay, is everybody all right with that? That's a little intro. Now, this chapter is, I don't know why, I'm not the author. I like the author of this book. I like the way they wrote the book. But I would have put these 2 pages in this chapter. So this next chapter, a test, would include chapter 7, but also, and you can write a little note in your book, it also includes the pages 452 and 453. So if you want to write a little note in your book, and you'll see this again tomorrow, I'm going to go back to that now. So I think I would have probably put those 2 pages in this chapter instead of way back there. So we're going to go visit that, and what I'd like to do is let's go to page 452. That's way back there. If you don't have your book with you today, that's okay. And you can probably see how many times I've given this lesson before, all the writing on my book. But what I'll do is I'll try to carefully go through all the steps that I wrote. And so what I'd like to do is, I don't have time to tell you everything that's so unique about water, but it's amazing. I also don't have today, I don't have time to tell you my story, but until I was right around 31 years old, I was an atheist. And I had, science was very big for me, and I'm going to tell you the whole story, but science almost kind of became my, not religion, because I didn't like the word religion, but it was, even if I didn't call it that. So all my trust and faith was kind of there in the science. That's why it was a miracle for me that God would ever be able to knock on the door and I would open it. Certainly there was a time when, no, there's no God. I was absolutely sure. That's just some story, and, people, they like thinking about it. But that was certainly a miracle for me that my eyes were opened, and before that, I would have just taught the lesson with water and said, here's the science of water. I am going to teach the science of water. But I have a little different feeling about it now, because the more and more I learn about this shouldn't happen. The stuff that water does, it shouldn't do that. It shouldn't do all those things. It's so special. And I thought about it, if you look everywhere so far in our solar system, and even other solar systems, we're not even certain there's hardly any water anywhere else. There might be a little bit, and we think there might be water there, a little bit. Maybe a little Mars, maybe a little bit. But where do we live? What kind of planet do we live on? If someone looked at our planet and said, that's a water planet. That's a water planet. It's like 80% of the surface, almost 75% of the surface of the Earth is covered with water. And then, what are you made of? You're at least 50% what? Water. To say that water is not important to us, that's ridiculous. What if I told you then, water is one of the most unique chemicals that I've ever seen. And we have a lot of it here, and a lot of it in you. And I don't see it very much anywhere else. There's something there. Something that, again, when I was an atheist, I wouldn't have thought that. That's water. So I'm going to try, if I can, I'm going to try to show you about the special properties of water, since the chapter is called what? Reactions in an aqueous solution. I need to know about water, because that's what aqueous means, dissolved in water. So if I know a little bit more about water, I'll know a little bit more about aqueous solutions. So here we go. First of all, I would say that all of you know that water is H2O. It's very, very possible that before you came in here this year, you might have thought it was H2O. No, it's H2O1, isn't it? Even though you say H2O, it's not two O's, is it? It's two H's, isn't it? Okay, so I think we learned that. Now, this is a nonmetal, and this is a nonmetal. If they form a bond with each other, what's the most likely kind of bond they're going to form? What do you think? Is it going to be ionic and make a salt? Is one of these guys going to lose electrons and become an ion? The other's going to gain electrons and become an ion? No, it's not an ionic compound. It's a what? Covalent compound. And what's the M word that means you're a covalent compound? Molecule. That's why in biology class in 9th grade, you heard that word a lot. Because what are the four elements that make up most of the living parts of a living thing? CHON, carbon, hydrogen, oxygen, nitrogen, right? Okay, so they're all nonmetals. And so if they form things like proteins, carbohydrates, lipids, and nucleic acids, aren't there the four big groups of organic molecules? And water is the inorganic molecule, H and O. They're all nonmetals. No wonder you heard the word molecule all the time in biology. If you became a geologist, you wouldn't hear it very often. Rocks are Those are almost all ionic compounds. So, anyway, the first thing I'd like you to know is that they are held together with covalent bonds. Okay, now, I'll take you back a little bit, and I probably did this a little bit in 8th grade, a little bit in 9th grade. If I look at the periodic table, how many electrons are in every atom of oxygen, for example? Whoa. How many electrons in every atom of oxygen? So we know this number 8 has 8 protons, and it's a neutral atom, so it has 8 electrons, doesn't it? Now, I don't know if you remember this, and I will do this, but before you get done, before the end of the year, we'll go all over this thing called electron configuration. Where are they at? And for example, this guy, I happen to know he has, of the 8, 2 of them are in the first energy level, and 6 of them are in the second level. I also know that because the Roman numeral right above this whole column is Roman numeral 6. That tells me that 6 of the 8 electrons are in the outermost energy level. Those are called valence electrons. You probably, does that word ring a bell to anybody? Okay. So you also may have known that the noble gases, except for helium, they all have something in common. Not the number of protons, not the number of electrons, but the number of electrons in their outermost energy level is 8. It seems to be that if you can put 8 electrons in your outermost energy level, you become very stable to the point where you don't want to gain or lose any more electrons. And so that's why they don't really react. They already have 8 in their outermost energy level. Oxygen has 6. It would like to gain 2. That's why in a compound, what charge does oxygen have? If you gain 2 negative things, that'd be -2. That's why we said oxygen column is -2. Hydrogen is unusual because it only has 1 electron, and it only takes 2 electrons in the first energy level to fill the first energy level. So it could do either. It could gain 1 or lose 1. Well, when it acts like a true nonmetal, it's going to want to gain 1. Okay, so now long story short then, oxygen wants to gain 2. Each hydrogen wants to gain 1. Okay, so what if I take your electron and 1 of mine? What if we were to share that pair? Now the pair means 1 of yours and 1 of mine. Could we share that pair of electrons? And the hydrogen says, well, I have 1, and if you let me share the other one part of the time, I'll have 2 in the first energy level part of the time. That's good. That's good for me. But oxygen says, it's better for me, but I wanted 8. I only have my 6 plus yours 7. I'd like to have another one. Well, I got a buddy just like me. And so I'm making it kind of a short story, but that tells you why water is not H4O. It's H2O. I need 2 hydrogens to form 2 covalent bonds with oxygen. Now, do you remember that from middle school? Have you remember something like that? If not, it's just a real quick story. Now, here's where God comes in. If he had made water linearly, if water would have been like this, if it would have been H-O-H in a straight line, none of the fantastic things that water does now would have happened. And yet I know many molecules like carbon dioxide, C-O-O, it's linear. There are many molecules that are linear. The fact that this is a bent molecule, that's important. Next, when they share electrons, and I have this little picture of a Snicker bar. I like Snickers. Okay. And the reason I have this little picture of a Snickers bar here is because what if Ethan, he said, well, I didn't have any lunch today. I said, Ethan, I have a Snicker bar. I said, is it okay if we share it? He says, sure. Now, then I take a knife out, and I cut off this little tiny piece, and I give it to Ethan, and then I eat the rest of it. And Ethan has this look on his face, and I said, what's the matter with you? I said I was going to share it with you, and I did. I did share it with you. But it was your fault that you assumed I meant what? You assumed I meant what kind of sharing? What do you think, Ethan? Yeah. Well, guess what? You're also making a mistake if you assume that God said every time two elements share electrons, they share them evenly. They don't. Now, if hydrogen were to form a bond with hydrogen, they would share evenly. They're both hydrogen. But God made it, this is the second thing he did, he made it so that one of these guys is more electronegative. Now, that's a fancy word for saying when we share electrons, my ability to pull them toward me is greater than yours. Now, that's important. I need everybody to look at me, okay? Number one, it's not linear. Number one, two, he made one of these elements, when they share electrons, it'd be greedy. Oxygen is more electronegative. It's more greedy. So guess what happens? When we share these negative electrons, where are they going to spend more time? Around the hydrogen or around the oxygen? Oxygen. And what charge electrons have? Negative. And same thing is going to happen over here, isn't it? And so we have a molecule that one end will have the electrons there more often than the other end. That sets up a neat situation. It's called a polar molecule. Now, in the world of chemistry, you'll see that word all the time, polar, nonpolar. Now, the only reason that we use the word polar in other areas, what is polar meant before today's lesson? If somebody said, I'm going to go to the polar regions of the world, where would you go? What? Yeah, South Pole, North Pole, isn't that right? It just so happens that our planet, the way it rotates around the poles. And the poles are the ends of the earth, aren't they? And it just so happens, on our planet, the polar regions are cold. Where do you find polar bears? See? Yeah? In the poles, don't you? Well, anyway, it just so happens, not every planet that we know of is it cold at the polar regions, okay? But anyway, so polar doesn't mean cold. It means at the ends. I have a battery here. What do we call these two things here? What do you call these two ends? Terminals or poles? It's not because it's cold. It's because there's something opposite about them, isn't it? One's positive and one's negative. If you said, I went to Page High School, and they asked me a question, and I told them that, and they were going to talk about, I said, well, let's talk about abortion today. And you would find out that the class quickly would be polarized. Cold? Or what would they do? What would I mean if the class became polarized with that topic? What do you think? You guys are smart. If you want to use a nice word in English and you want to impress you, say, here's comments, polarize the group. Polarize means that about half, or not even half, but a certain said, well, I agree. And somebody said, I disagree. That's how they were polarized. So this is a polar molecule because one end will be slightly, not a full negative charge like an ion. It'll be partially negative, and the other end will be positive, slightly positively charged. All right, now what I'm going to do is, I'm going to show you some fancy words here. What kind of a bond holds, is it intramolecular bonding for water? What kind of bonding is intramolecular? Intra means within. Within one water molecule, what kind of bonding is it? And I just told you what they were. What are they? Max, you know. Covalent. They are. Now, because they're covalent, because they don't share evenly, we're going to give it a fancier name, polar covalent bonds. They're polar covalent, or sharing, but not equally. Get that? So we have a polar covalent bonds here, and that ends up having a molecule, which is a polar molecule. Now again, if you'll listen carefully, I'm going to tell you how unique water is. And God, if God had not done this, that's two things so far. Let me tell you what else is going on. Okay, so now, what do you think would happen if I took a water molecule and put it next to another water molecule? What if I took a water molecule and put it next to another one? Now, I ran out of space last year, so I had to draw it down here. So here's a water molecule, And remember, the oxygen end is slightly negative and the hydrogen end is slightly positive. What would happen if you had water next to another water? And I want you to think about this. I'm a polar molecule, well, so am I. Which part of the water molecule would also be attracted to another part of another water molecule? Do you see that happening? And so that the oxygen end of this one would be attracted to the hydrogen of another, and et cetera, and et cetera, et cetera, et cetera, et cetera, et cetera. So in a glass of water, all the water molecules that are close to other ones, they're probably pushing themselves around trying to be attracted to another water molecule, and that's called intermolecular bonding. Now they have a special word for that, and I don't know if Ms. Founds used that with you guys or not. But the kind of bond that occurs between molecules, intermolecular for water, is called a hydrogen bond. You remember? You might not have ever mentioned that. Okay. I'll bet she did do this. I'll bet she talked about DNA. Do you remember DNA? And you remember A, T, C, and G? And remember how they talked about it being like a ladder? And they had the rungs of the ladder. A is here and T is there. Remember that? Did you ever wonder the strands of the ladder are held together with very strong covalent bonds, very strong. But what is it that holds A attracted to T? Why is G attracted to C? And believe it or not, it's hydrogen bonding. Now, hydrogen bonding is not as strong as some covalent bonds, but what if you had a whole bunch of ATs and Cs and Gs like that? They could hold itself together, but guess what DNA can also do? Remember the chapter where DNA replication took place? And they discovered that DNA has to do what? Doesn't it unzip? You have to break those hydrogen bonds, and then this strand of DNA makes a copy, and so do I. And when we get done, we have two copies. We have two pieces of DNA that are identical. Do you remember that story? Or was that during COVID? Okay. Anyway, so those are hydrogen bonds also. Hydrogen bonds are kind of neat. Okay, so let's go back to this other page here, right here. So my question is, why is water so good at dissolving things? Water is called the universal solvent. Now, that does not really mean it can dissolve everything. It can't. But it dissolves a lot of things. So here we go. Does anybody recognize this? Anybody have an idea what this might be? And we can read the caption. It says, polar water molecules interact with the positive and negative ions of salt. So the salt they're using is table salt. And so look at what table salt would look like if I could see it. None of these would be neutral atoms. None. They'd all be ions. I've already lost electrons. I gained electrons. And so which one would be the sodium ions? The green or the gray? Which one would be the sodium ions? Can you see the little plus and minuses on there? Can you see the plus and minuses? Okay, so what do you think that is right there, a plus ion? In table salt, who's the positive ion? Which one? Sodium. It is. Metals tend to become cations, don't they? So these are sodium ions, and these are chloride ions. You get it? And that's what makes up table salt. So when you see a little grain of salt, it's really a bunch of ions holding themselves together with ionic bonds. Now, those are very powerful bonds. They're very powerful. But what happens when I take a piece of salt and I throw it into a glass of water? What happens if I take a little crystal of salt and I throw it in water? Why is it that it looks like it disappears? It looks as if it disappeared. Now, what happened to it? And so here's the story. Water is polar, is that correct? So it has a plus-minus nature to it. Salts have a plus-minus nature to them. They have a plus, right? And likes dissolve likes. So water being polar has a plus-minus nature, and you have a plus-minus nature. So here's what's going to happen. What which end of water would be attracted to these big old negative chloride ions? Which end of water would be attracted to the chloride ions? The hydrogen end or the oxygen end? I need everybody to think. I asked you today to do some thinking today, right? I told you this is already a higher level chapter. We can do it. Which end? Which one? Right, since the oxygen electrons, the negative electrons spend more time around oxygen, so that end is negative. And so negative is not going to be attracted to negative. So look at the drawing they did. Notice that when they come over here, what happened to this chloride ion? Hey, how come you're not in the crystal anymore? Who pulled you out of the crystal? And so here's one water molecule with the hydrogens being attracted, and another, and another, and another, and another. And so there's a battle. Now watch now. Before I put you in water, you had a strong bond between plus and minus ions. Then the water comes along and says, I'm going to try to attract you. Well, who wins? If I put salt in water, who wins? The ionic bond or the hydrogen bonding? The attraction of water to this ion. And the theory is that this water can surround the chloride ion and pull it out of the crystal in like, a millionth of a second. Another one, another one, another one. And what about the sodium ions? Look at the drawing down here. What end of the water molecule is going to be attracted to the positive sodium ion? And it would be the oxygen, because that's the negative end, isn't it? And so the plus and minus nature of water makes it really good at dissolving ionic compounds that have a plus and minus nature. Are you with me so far? Some of you look a little bit more tired. Maybe? Okay. Anyway, I want to try to show you that picture. And it's not that I won't go over this again. I can go over it again. So I think it's amazing that we have this much water on the planet, and our life is absolutely dependent. They estimate that not all of us, but a lot of us could actually go maybe up to 30 days with no food. But how long can you go without water? Maybe 3 days, 4 at the most, maybe. Why is that? Why is that? And so we know that water is always going to be important to this type of life on the planet. And yet, I don't know where else a whole lot of water is. Where else? What other planet? I don't know. So far, I don't know. Okay, now let's go over here, and I'm going to get a little more complicated here. Here we go. You can do it. Take a look at this next picture. Do you think that what other kinds of things might dissolve in water? We know that ionic compounds, many of them, most of them, will dissolve in water, and we understand why. But what about something like this? Now, you haven't had enough chemistry to know what these are, but this is called an alcohol. Okay? Now, this is an alcohol, and the reason I know it's an alcohol because it has a carbon, oxygen, hydrogen right here. This COH right here, this COH, first of all, this is an organic molecule. Okay, organic means that I'm a carbon compound. You get it? Now, your salts are your metal and nonmetals, aren't they? These guys are nonmetal, nonmetal, nonmetal. These are molecules. So what would make some molecules dissolve in water also? Not all of them do. So take a look. I'll tell you that an alcohol has this COH in it. What happens when O and H bond together? What kind of bond is that together? What kind is that? What kind of bond does O and H form? Non-metal, non-metal, covalent, even, or polar in nature? Is it going to be even sharing of electrons? I don't think so. Oh, so you're going to have this end of the molecule is going to be polar. So, alcohols are polar molecules. Water is polar. Do you think alcohols dissolve in water? Likes dissolve likes. Would you think polar alcohol would dissolve in polar water? Yes. Now, I have a bottle back here, and I went to the store and got it because we needed it for an experiment. And it says isopropyl alcohol, rubbing alcohol. Everybody know what that is? But on the bottle it says 70% rubbing alcohol. What's the other 30%? Water. When you buy vinegar, it says 5% acetic acid. What's the other 95%? Water. And so I know that alcohol is dissolved in water. I know that. Now, I'm not getting too much into this, and if you want to ask your parents, you can, but there's many alcohols that if you were to drink 100% alcohol, you could actually die. I mean, really die. And I think it's kind of weird that God even allowed any of the alcohols to be ingested and not kill you immediately. But we do have different alcohols that people use for different things. Beers have alcohol in them, wine, and then they'll have your hard liquor, that kind of thing. And they have these terminologies. Like, for example, they'll say it's 120 proof or 80 proof. Well, I know where the story came from, but I don't know why they had to use numbers like this. But if you were to have a bottle of 120 proof alcohol, if you cut that number in half, it means 60% of that is alcohol and 40% is water. That's huge. Now, a beer or a wine might be 5, 6, 7, maybe all the way to 13 for some wines. So 5 to 13% alcohol is beer and wine, which that can mess people up too, can't it? Can you imagine people drinking something that is 60% alcohol? And you think, no wonder they got messed up. You're right. Well, anyway, I just want to make sure alcohols do dissolve in water, and if you ever see that word, if it's 80 proof, it's 40% alcohol. Got that? Okay. Now, so we know that because alcohols have this COH, and this makes it polar, that polar things dissolve in polar. All right, let's try another one. How many people think sugar dissolves in water? Okay, now, the sugars that you know of in biology class, there was glucose, and glucose was C6H12O6. What kind of bonds do you think hold glucose together? Well, let's see, non-metal, non-metal, non-metal. It's all covalent, isn't it? Got it? It's all covalent bond. But if you look at the structure of table sugar happens to be sucrose. It's C12H22O11, and you say that's still a whole bunch of covalent bonds, right? But let me look at the structure. Carbon, 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 oxygen. What? H, OH, H, OH, H, OH. There's that OH thing. What kind of bond is holding the O with the H? What kind of bond holds O with H? Non-metal, non-metal. What is everybody? Everybody. Covalent. Even? Even sharing? I don't think so. So guess what? This part of the sugar molecule and this part and this part and this part, all those are polar ends. They're polar parts of the molecule. So what happens when you put sugar in water? Is it going to dissolve or not? There's nobody in this room that doesn't know the sugar dissolves in water. Isn't that right? Right? Okay. One more. I'm going to close this story down a little bit. But let's take a look. Yes?
So in a molecule, it can have polarized ends?
It can have parts of it that are polar, yes. It can have parts of it that are polar. Let me tell you, in biology class, I'll bet you remember this. Maybe not. Do you remember some little drawing, and they were talking about the cell membrane, and they drew these funny things that you thought were balloons? And they had another row of balloons like this. And that's why, even though we take biology in 9th grade, you probably understand it more if you'd had chemistry first. Do you remember what that is? Remember the cell membrane? Remember they said the cell membrane, what was it made of? Remember they said it was lipids and proteins? Okay, let me show you something about some of those lipids that you had, all right? One end of the lipid molecule was non-polar. I don't like water. Hydrophobic. I don't like water. Okay, I'm sorry. I don't like water, my fault. And the other end was hydrophilic, polar. I like water. And so what happened is you have a row of molecules that are polar, nonpolar. And over here, polar, nonpolar. So here's the outside of the cell, which has lots of water in it. And where else is water? Inside the cell. And so the parts that didn't like water, they were stuck in between. They didn't have to get in contact with water. And so those little things were what they call phospholipids, which meant one end liked water, one end didn't like water. So I like your question. You mean you can have a molecule where one end likes water, one doesn't? They do. Okay, now, let's go this one last thing into here. There are some chemicals that are called hydrocarbons. What do you think hydrocarbons are? Take a wild guess. What do you think they might contain? Carbon? Yes. What else? Hydrogen? Yes. That's it. If you're a hydrocarbon, this is almost all pretty even sharing. Even sharing. And so guess what? None of the hydrocarbons are polar. No part of it. It's called a non-polar molecule. So what would happen? Vegetable oil is a hydrocarbon, essentially. And so there's nothing polar about it. So what happens when you mix vegetable oil and water? If you mix it in a glass and let it sit there, what's going to happen? All the oil will come to the top and all the water will go to the bottom. They won't mix because water's polar and oil is non-polar. Gasoline and water, they mix? You ever done it? I have. You ever put some water and gasoline together? You know what gasoline's made of? Carbon and hydrogen. It's a hydrocarbon. That's why it won't mix. It's non-polar. So I wanted to show you that the fact that you knew, the only thing I'm going to ask you that's non-polar are probably hydrocarbons, okay? The things I do want you to know that are polar, ionic compounds have a plus-minus nature, so they're going to dissolve in water, most of them. The alcohols have a polar nature, don't they? At least one end. And sugars have many ends that are polar, so they tend to dissolve too. All right, what do you think about this story about water so far? I haven't even gotten in. I'm not going to get into the physics of water until you take physics class. But I'll tell you, I only have a couple more minutes. Let me tell you real quick something else about water that has nothing to do with chemistry class. You got it? Okay. There's this thing in physics called specific heat. And what it means is how much heat do you have to absorb before your temperature goes up a degree? Now, we have things in my home, in your home, that have really low specific heats. They're called like aluminum and iron, and they make pots and pans out of them. Why? Because when I put that pan on the stove, a little bit of heat from the stove, a little bit will make that metal change temperatures quickly. It has a low specific heat, so the heat's going to get cooking my egg pretty fast. What's the worst material you could make a pan out of? And it's water. Water has one of the highest specific heats of any material on the planet. So what? I'm not going to make a pan out of water. But so what? Think about this. What happens when the sun is shining on the earth? It should cook you. But you have an atmosphere that has a lot of water in it. So the water absorbs, and just, it takes a lot of heat before it'll change temperature. You get that? And at night, you should freeze to death. But guess what? All that heat that was stored in water, it releases slowly. We're alive. Now, if you go to Arizona, they have almost no humidity in their air. What happens in the daytime? You get really hot. And what happens at night? You're not going to believe this. You will freeze to death in Arizona desert. Now, if I were lost and I didn't want to freeze to death at night, I'd probably go into a woods. More humidity, it must have stored more heat. Now, it is true, it took longer to heat up the forest during the day. But what happens at night? It takes longer to cool off the forest because it has a high specific heat. That's just one of those unique things about water. I've already mentioned about 3 or 4 so far. I hope as you walk out today that you think a little bit differently about water. This whole chapter is about solutions, isn't it? Okay, so tonight, I'd like you to read maybe the first 5 pages of chapter 7, and make sure you bring your book tomorrow, and then we'll get into this chapter a little bit deeper. All right, I think that's it for me.